Let us look at proposition number 49 of book 10 of Euclid's Elements. The proposition says to find the second binomial line. In the previous proposition, we saw how to find the first binomial line. So now we are talking of second binomial line. And naturally, the question is, what is a second binomial line? So let's look at the definition. Given a straight line and a binomial divided into its terms, such that the square on the greater term is greater than the square on the lesser by the square on a straight line commensurable in length with the greater. Up till here, it is the same as definition for the first binomial line. Now for the second one, this is where the difference comes. Then if the lesser term is commensurable in length with the rational straight line set out, let the whole be called a second binomial. So the difference between the definition for first and second binomial lines is that in the case of the first one, we are talking of the greater term is commensurable in length with the rational straight line set out. Here we are talking of, in case of second binomial, the lesser term is commensurable in length with the rational straight line set out. So having understood this, let's see how to arrive at this second binomial line. Let me get rid of all this because we have to arrive at this. So set out two numbers AC and BC such that AB is to BC is equal to number square is to number square, or what we would normally say, let AB and BC have a ratio which a number square has to a number square, and AB is to AC does not have a number square is to number square ratio. So let me bring in these A, B and C. So AB and BC have a ratio of a square to a square number, and AB does not have to AC a number square is to number square ratio. Set out a rational straight line D. Let EF be commensurable in length with D. So we take a multiple of D. Here, if you notice, D is a rational straight line. That means D is rational. And since EF is commensurable in length with D, that means EF is rational. Let AC is to AB is equal to EF square is to FG square. Now here, we do not have FG square. We don't have FG. So we can't have a square on FG. We have to find that. So, and we have to find it in such a way that it satisfies this proportionality. AC is to AB as the square on EF is to square on FG. We know how to do this. So let's construct it. Now, since AC is to AB is equal to number is to number, because remember, AC and CB are numbers. And because of this proportionality, it means EF square is to FG square also has a ratio that a number has to a number, which basically means that EF square is commensurable with FG square. And since EF is a rational, that means FG is also rational. Now, EF square is to FG square does not have a number square is to number square ratio. So that means EF is incommensurable in length with FG. That means EF and FG are rational straight lines commensurable in square only, which basically means EG is binomial. Now AC is to AB is equal to EF square is to FG square. So inversely we can say AB is to AC is equal to FG square is to EF square. And AB is greater than AC, naturally, because AB is the sum of AC and CB. So AB is greater than AC, which means, again, because of this proportionality, FG square is greater than EF square. Let EF square plus H square is equal to FG square. Now, if you notice, H square we don't have. So we have to find H such that the square on that plus the square on EF is equal to the square on FG. Again, we know how to do that. Let's look at this proportionality. We have AB is to AC is equal to FG square is to EF square. So let's do the conversion. In conversion, AB is to the remainder, right? So AB is to AC, so AC gets replaced by the excess. So AB is to BC is equal to FG square is to the excess, that is H square. Now, since AB is to BC has a ratio which is number square has to a number square, because of this proportionality, FG square is to H square also has a ratio of number square is to number square, which means that FG is commensurable in length with H. Now look at this, EF square plus H square is equal to FG square. We can rewrite this as FG square is greater than EF square by H square. So what does this mean? FG and EF are rational and EF is commensurable in length with D, right? This is what we started off with. Set out a rational straight line D, let EF be commensurable in length with D. So we have FG and EF are rational and EF is commensurable in length with D, which means EG is a second binomial straight line. Now let's revisit this definition and see whether it makes sense. Given a rational straight line, that is D, and a binomial divided into its terms, so we have EF and FG. So EG is the binomial divided into its terms EF and FG, such that the square on the greater term, FG square, is greater than the square on the lesser by the square on a straight line commensurable in length with the greater. So FG is commensurable in length with H. Then if the lesser term is commensurable in length with the rational straight line set out. So lesser term is EF. It is commensurable with a rational straight line which we started off with, that is B. Let the whole be called the second binomial. Here whole means EG. So EG is a second binomial straight line. So that is proposition number 49 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.